Thanks for watching my channel, Terms of Living. Today we're going to be talking about Ohm's Law. I've been dealing with electronics professionally and sort of as a hobby for, decades now. And to me, these things, these real basic things are second nature. Sure, there's a lot of material out there on the edge like Laplace and some control stuff. It's got me a little, it's where the edge of my knowledge goes. But I wanted to share how I have come to view this stuff. And what we have before us here is two of the common derivations. And it's a standard algebra, so you can flip these things around and you can play some interesting games with this. But before I even talk about these calculations, I want to try to get a more fundamental sort of understanding of what is happening here before even trying to talk about the math, because what I'm trying to get at with this video is to get some sort of intuitive sense of what's going on with Ohm's Law. So basically we can talk about, to a limited extent, electronics or electricity as flow of water or whatever kind of liquid you choose through a pipe. And here's something we have on our house. This is just a spigot. This would be the house side where the water pressure is, and this would be, where you get your water from. And basically, looking at this, taking this as the condition where this, let's say the spigot's off. One thing we can say right away is that the pressure on this side is at its maximum compared to the pressure on this side. Under the normal operating conditions here, that's the case when this is shut off. Take the opposite extreme case when this is completely open. Given that, ignoring whatever resistance this fully open presents to the flow, the pressure on this side would equal the pressure on this side, which would equal the pressure anywhere along this pipe, making this basically transparent, in an ideal case, of course. And then, of course, if you ratchet that down a little bit, then you're going to have some differential here, and of course your flow is going to be affected. And what I'm saying is that this is exactly what Ohm's Law is saying is going on in electronics. Now, to pin it down a little bit, let's say that we have somebody over here and they have some sort of requirement. In order for them to be happy and go on with their lives, they need some amount of water. Let's just some arbitrary number like a gallon every 2 minutes, say. Well, we know right away when we say there's a gallon every 2 minutes coming out of here that we know that the amount of water is fixed. It's how much water is coming over the course of 2 minutes is 1 gallon, and that's it. And that's a spec that's set forward. On the other hand, we have over here an uncontrollable factor, or at least a fixed factor that we are not dealing with controlling, which is the water pressure. So what we have is we say we want some fixed amount of water, some fixed flow, some fixed current. We're dealing with some fixed pressure, and all we have to alter and deal with that is the spigot, the resistance to the flow. So by adjusting this, we can come up with a continuum of amounts of flow out of here. And we can shut it off or open it all the way or go for that specific point. Now, if we know that the water pressure here is always the same, we could actually graduate this, right? We could say, well, at this point, this is this much water flow. But of course, even in the same building or the same house, the water pressure can change. But the point is that really it's sort of its own whole system, and we say there's pressure and there's current and there's resistance, but really they're all pinning each other down. So the idea of Ohm's Law is saying, well, look, if you're gonna say you need this over here, then we have to know what you got over here, and then we can set that. Or if you had some strange circumstance where the pressure was changing, then you could with a fixed, if this was fixed and you couldn't adjust that, then you could adjust the pressure and come up with the same sort of results by the amount of pressure through this resistance. Now, just bringing this back, right, because we're talking about electronics, is here's a representation of basically what we've got here. What I have here is a simple circuit with voltage, a resistor, sorry, and this is a sort of a black box, right? Let's say this is an LED, just so that we have something concrete to think about. But this would be an LED, one powerful LED, by the way, at 0.1 amps. Okay, so let's say we have a requirement. It's an LED. We need 1 amp of current flow through it. So what do we have? We have a current flow of 1 amp, right? We can say we have a current flow of 1 gallon, right? 1 gallon for every 2 minutes. So the numbers are not important down here especially, but that we both have a demand here. We're dealing with a fixed pressure. Let's say this is 10 volts, right? Let's just, so that we can nail that down. So we're not going to be calculating hydro, whatever this is. I'm not a water hydraulics guy. Anyway, so we have pressure, which is going to be 10 volts, and that's what voltage is. Voltage is pressure pushing electrons through the atoms of a substance, and that's exactly what voltage does. We have a resistor, which could be variable, right? You might have seen something like this in a schematic. That means a variable resistor, actually. So now we're very close to this approximation, and what we can do is we can adjust this resistor. This could be some range of ohms, whatever. Now, just looking at this, I know that we would need 100 ohms here, just because obviously I've looked at this. But what we have here is we're pinned down here. If we're saying we need 0.1 amps and we're using 10 volts, we're pinned down. We have no choice. Ohm's law just allows us to go find a resistor that's going to be generally fit what we're looking for there. And the calculation would be, again, going back to this original Ohm's law diagram, an iteration that's not here, or a version, would be V over I equals R. So you'll have to rewind that if you didn't catch it, but the math is the minimum part. It's a requirement, but it's a minimum part of this presentation. So let's say V over R over I, which equals R. So this is actually going to be 10 volts over 0.1 amps, and this is going to be 100 ohms, right? So in order to get this LED in its operating range, you have to put a 0.1 amps through it, and based on 10 volts, you're going to have to supply a 100 ohm resistor. You have no choice. Now you can put 120 ohm maybe, or you can vary a little bit there, and this LED is going to work just fine. And in fact, that's what you have when you come up with an exact resistor value. You're always going to have to choose a value closer. Higher or lower is going to be based on the situation. But basically what you have here is you have this dynamic. Now, I left something out for some of you who might say, hey, you forgot about the voltage across the LED. There would be a voltage here. So I can talk about that at another point, but that's not at the core of what I'm saying, because I could have just used another voltage that incorporated this for you people who want to make a big deal out of it. Anyway, so the idea is that you have pressure, voltage, you have resistance, and then you have current flow. And that's what Ohm's law is. And Ohm's law is just a relationship of how do you get to one being pinned down with the other. Maybe you have a circuit where you have a resistor and you have a voltage. Now you have to find the right LED. Maybe you need an LED that has a certain rating. So it's not that, I found the resistor I want. It's that I have a sense of how to determine what's supposed to be what, given other things. Now, if I don't have anything here, I can just make up any numbers that I want. Of course, most of the time you're actually going to be working with 12 volts or 5 volts or some other, those are the most common voltages you're going to be dealing with. I wanted to give one other interesting example. If we do 10 volts divided by 0 ohms, we get infinity, right? When you see infinity in a calculation, that means burning up resistors and smoke and stuff. Thank you very much for watching.